Having understood the process of diagonalization, we now focus on diagonalizing symmetric matrices. Symmetric matrices play a very important role in pattern recognition problems, and therefore we need special focus on this. Now, the basic points are the mathematical preliminaries behind diagonalization of symmetric matrices have to be understood. Now, all of us know by definition a symmetric matrix should satisfy A is equal to A transpose. Eigenvalues of a symmetric matrix are always real, and a square matrix A is said to be diagonalizable if it is similar to a diagonal matrix. Every symmetric matrix is diagonalizable. And very importantly, if the matrix A is symmetric, obviously the eigenvalues are real. The eigenvectors corresponding to distinct eigenvalues are orthogonal. And every square symmetric matrix is orthogonally diagonalizable. That is, there exists an orthogonal matrix P such that P inverse AP is equal to D, but when P is orthogonal, P inverse is P transpose itself. Therefore, one can achieve diagonalization using P transpose AP is equal to D. The diagonal entries of D are the eigenvalues of A. And finally, the column vectors of P are linearly independent eigenvectors of A that are mutually orthogonal. So the key point in orthogonal diagonalization of symmetric matrices is to ensure that P is orthogonal. That is, all the column vectors of P, of course, all the row vectors of P should be orthonormal. Now, what is the procedure by which we can orthogonally diagonalize a symmetric matrix? First, determine the eigenvalues of the symmetric matrix A and determine the eigenvectors of A. Now here we have to be careful. If the eigenvalues are distinct, then the corresponding eigenvectors are mutually orthogonal. That is, suppose we have lambda 1 and lambda 2 which are distinct, then the corresponding eigenvectors x1 and x2 will be mutually orthogonal. But when there is an eigenvalue with a multiplicity, that is when it's repeated, there is a possibility of building eigenvectors which may not be mutually orthogonal, but that should be avoided. So using the Gram-Schmidt process, you try to ensure that all the vectors that we get as eigenvectors are mutually orthogonal. You store the orthonormal vectors in the matrix P. That is, not only should you find orthogonal vectors, you must also make them of unit length. That is called the process of normalization. And then once the matrix P is built, you diagonalize the matrix A using the rule D is equal to P transpose AP. Now let us go through two examples. So once again, let us remind ourselves that we are focusing only on symmetric matrices in this lecture. The first matrix that has been selected is the matrix 0, 0, minus 2, 0, minus 2, 0, minus 2, 0, 3. Now one can check that this is a symmetric matrix. And then you find the characteristic equation, lambda cube minus lambda square minus 10 lambda minus 8 is equal to 0. And when you factorize this or solve this equation, you get distinct eigenvalues minus 2, minus 4, minus 1. Now this is possibly one of the simplest cases of orthogonal diagonalization because we know distinct eigenvalues will return distinct eigenvectors which are mutually orthogonal. So let us start with the A minus lambda I into x is equal to 0 homogeneous system and plug in the value lambda is equal to minus 2 first. When we find the rank of this coefficient matrix, the rank is 2. We can have only one eigenvector, and that can be found as 0, 1, 0 by using the method of cross multiplication on two linearly independent rows. Be careful that in this determination, the second row should be avoided because it's a 0 row. So you apply the method of cross multiplication on the first and third rows to get 0, 1, 0. When we plug in lambda is equal to 4 and repeat the process, again the coefficient matrix will have rank 2. Therefore, again we have one eigenvector, in this case minus 1, 0, 2. Finally, lambda is equal to minus 1 returns the eigenvector 2, 0, 1. And we normalize all the three eigenvectors by dividing with their norm. And then, for example, if you take the first eigenvector, it is 0, 1, 0, it's already of unit length, so no normalization is required. Whereas, when you take the second eigenvector, minus 1, 0, 2, the length of this vector is root 6, therefore you will have to divide that with root 6, and then the last one, root 5 rather, and the last vector also will have length root 5. So divide all of them by root 5 and the matrix P is ready. One can check that P is orthogonal by verifying P into P transpose is equal to I. Now coming to the last stage of diagonalization. So let us perform the serial multiplication P transpose AP, and then using your calculating instruments, you can find that I get a diagonal matrix with minus 2, 4, minus 1, which are the eigenvalues on the diagonal. So this is how we have explained, we have understood the process of diagonalization of a symmetric matrix with distinct eigenvalues. Now the second example yields eigenvalues which are repeated, one eigenvalue repeated. So let us take this matrix, find its characteristic equation. We get lambda cube plus 18 lambda square plus 81 lambda plus 108 is equal to 0, yielding the eigenvalues minus 12, minus 3, minus 3. So build the homogeneous system A minus lambda into x is equal to 0. First plug in lambda is equal to minus 12. Find the rank of the coefficient matrix, you get rank 2. And we get one eigenvector minus 1, 2, 2 by using the method of cross multiplication on any two linearly independent rows, maybe the first row and the second row. Now you have to be cautious because we are approaching a lambda that is repeated. Lambda is equal to minus 3. And then when you find the coefficient matrix rank, the rank is 1. Therefore, we have n minus r, that is 3 minus 1, two eigenvectors corresponding to lambda is equal to minus 2. But you must be careful that the two vectors you produce must be again orthogonal to minus 1, 2, 2. You can use the Gram-Schmidt process, and then you can build a matrix P like this. Remember, the first eigenvector minus 1, 2, 2 has got a length 3. Therefore, you'll have to normalize that vector by dividing with 3. So the other two vectors of lambda is equal to minus 3 can be built as 2 by root 5, 1 by root 5, 0, minus 2 root 5 by 15, 4 root 5 by 15, and root 5 by 3. So let us see the P transpose AP, and then the details are not shown, but when you multiply using your calculating instruments, you get a diagonal matrix. So this lecture should convince you that every symmetric matrix is diagonalizable, irrespective of whether lambdas are repeated or non-repeated. So this plays a very, very important role when we actually come to some pattern recognition problems. I hope the concepts have been understood.